is the maximum shearing stress criterion. And this is usually known as Tresca. And let me teach you how to remember that maximum shearing stress Tresca. So to spell Tresca is T-R-E-S-C-A, right? That's how you spell Tresca. So shearing stress, the symbol is what? Tau. So when I spell Tresca, I deliberately put a what? I deliberately put a tau. The T I transfer it to a tau. So it's straightforward, right? Tresca I replace with a tau. So I know Tresca is always based on what? Maximum shearing stress. Just something on the side to help you remember. If someone asks you, I'm going to use maximum shearing stress, you will automatically reflect, oh, yeah, Tresca is maximum shearing stress. Or some questions that might confuse you, use Tresca criteria, you will say, Tresca criteria uses what? You cannot remember. And then you know Tresca start with T, the T look like a tau, so maximum shearing stress, okay? And the other criteria, the second criteria, which is commonly used, is what we call the maximum distortion energy criterion. And this is based on what is, I mean, not based, but this is what we call Vomices. Some of you want to pronounce it Vomices, go ahead. I'm not bothered. Okay, criteria. Okay. So these two are commonly used. So maximum shearing stress, and you have maximum distortion energy. Right. So let's look at maximum shearing stress criteria. Yeah, let's look at maximum. Okay, maximum. Oh, I have problem spelling now. So let's look at maximum shearing stress. Criterion. Right. So we have tau max, or we call this under Tresca. Where tau max is equal to half the maximum stress. Okay. So this is Tresca. So when this is the case, okay. So now this tau max is equal to sigma max divided by 2. It is only possible when one of the principal stress right? When one of the principal stress is equal to 0, okay, and the other can either be positive or negative. Okay, so what does this mean? Okay, so if we have to sketch this out, okay, we have to sketch this out. So you have this is your normal stress. This is your shearing stress. Element rotate clockwise, anti-clockwise. So one of the principal stress, okay, so this is stress A, is at 0, and then stress B is over here. Okay. So for this case, when we construct the Mohr circle, oh, too much. Right? So tau max, or the maximum shear, will be equal to stress max divided by 2, right? So this is equal to stress B divided by 2, okay? So one thing I want you all to take note is stress A. So now when we use the U criteria, you will see this quite often where stress A and stress B, not 1 and 2 anymore, are known as principal stresses. So i.e. the shear is equal to 0 at point A and point B. Okay. Now another equation that can be used, okay, in Tresca is where tau max, the maximum shear, right, will be equal to half the absolute value of stress max minus by stress mean. So this is the other condition. Okay. So when this is the case, when the principal stress right are positive or negative. By the way, this tau max over here, okay, this is a material property. Okay, your tau max over here, they are based on your material what? Property. Over here, what you see over here, oh, this is a bad way of doing it. This over here is your calculated based on structure analysis. Okay, so this is also what? This is also your calculated. Okay. So now for this case, if we were to draw this now, so what we are saying is this. So now the stress A and stress B is not equal to 0. Okay, so this is our normal stress, and this is our shearing stress. Right? So for this case, we have our 2 points. So we have, this is our stress A, and over here, this is our stress B, right? So 2, 4, 6, 7, 3.5. So we construct our circle. Right? So for this case, the radius, okay, so 3, 6, 7. So this is the where our radius is, or our center point is our stress average. Right? So what we calculate in stress max minus stress mean is this value over here. So if we were to I were to do this, so the distance from here to here, right? The distance from here to here, this is equal to stress max minus by stress mean divided by what? 2. Okay. So again, I do. Some of you might be confused. Why is it stress? So this is the radius. Okay, to calculate the radius, right? From here to here, this is stress max minus my stress mean divided by 2. Okay, some of you will ask me, Eugene, we ever seen stress max plus by stress mean divided by 2? Why do we go? So if you decide to calculate stress max plus by stress mean, I'll use a different color. Okay. The distance from here to here is known as our average stress, and average stress is equal to stress max plus by stress mean divided by 2. It's not the same thing. Okay. All right. So for this case, tau max, so this is our tau max value. So if that's the radius, the distance from here to here is our tau max. Right? So the distance from here to here is equal to our tau max, and this will be equal to stress max minus by stress mean divided by what? Divided by 2. Okay. So in Tresca, I'm going to draw the operating bracket. Okay, we're going to draw the operating bracket of Tresca yield criteria. So I'm going to construct a different graph now. Okay. So what we see now is the x-axis is the principal stress A, and the y-axis is going to be principal stress B. Okay. So this is our stress A, and this is our stress B. Okay. And then stress A and stress B, we will be going over here. I'm going to make 4 marks, right? So this is stress yield, and this is minus stress yield. Okay. Again, this is stress yield, and over here, this will be equal to minus stress yield. So for Tresca criteria, we usually assume that the stress in yield in tension is equal to stress in yield in compression. So this is tensile or tension, and this is compression. They are the same. In reality, in real life, it is not the same, right? In reality, the material can withstand much higher stresses in compression when compared to tension. Okay, so Tresca sketch. Now, this is stress A and stress B. These are the principal stresses. Okay, and then he sketch or he developed an operating boundary. Okay, so this is the operating boundary. Right, and then he construct the yield in the other quadrant over here. So if your stress field is within this boundary, okay, if your stress field is within this boundary, where the shaded region, so when stress A and stress B are within the shaded region, the material will not yield. All right. But if outside the shaded region, the material will yield. Okay. Right. So what I'm going to do, I'm going to stop here for now. When we come back on Thursday, I'm going to explain to you what does this operating region actually means. Okay. Why within the shaded region is valid, outside the shaded region is not valid. Okay, so I'm going to stop here. Now, on Thursday, you're going to have the quiz, and the quiz is going to be from homework number 8. Okay, again, the quiz will be from homework number 8. If that's the case, I'm going to end my lecture here. Anyone, any questions, please? Anyone? Oh, good. Okay, if that's the case, I'll end my lecture now. Thank you for your time. Thank you.